Good morning. I am Joseph Reddy, an AI consultant focusing on artificial intelligence applications, primarily for health science and manufacturing. On the slide, you're seeing my website. So if you navigate to this website, you will see information how to get in touch with me either by phone or email. Today, I'm going to talk to you about a system, a proof of concept to implement a retrieval-augmented generation system on a large language model, Llama 2, using resource-constrained hardware. So it could be RTX 2060, which is the development platform I've been using, or Google Colab that I'm going to demonstrate in a moment. So the goal of my proof of concept is to assess whether we could effectively combine Llama general knowledge with custom domain data while running on consumer-grade hardware, specifically a PC with an RTX 2060 or Google Colab. After evaluating several options, we chose Llama 2, 7 billion parameters, as the base model. Earlier experiments using GPT-2 and T5 were not suitable for the requirements. The diagram on the right-hand side of the slide illustrates the knowledge sources for the demo. I'm working with content from financial publications like Wall Street Journal, Barron's, Frankfurt Allgemeine, showing how RAG enables me to enhance the model's responses with domain-specific knowledge. We implement this using a modular, simple RAG class architecture, which makes the system flexible and adaptable for different use cases. Here you see some detail on the technology stack, which is all from open source. Llama 2, 7 billion parameters is the base large language model. Hugging Face transformers and sentence transformers are used for model handling and embeddings. Facebook AI similarity search, you see FACE acronym in the slide, provides vector similarity search. PyMU-PDF is a tool, again from open source, to handle PDF document processing, namely converting PDF into text. So the code is available in GitHub, and the hyperlink will take you to the GitHub repo. And it can be deployed in Colab, as I'm going to show in a moment. So on the right-hand side, you see the system flow. The blue boxes represent the inputs, PDF documents on the left, and the user query on the right. PyMU-PDF extracts text, which we truncate to the first 1,000 characters. This is one of the assumptions I made to implement the system. All MIDI LM L6 V2 is an embedding model that converts the text into numerical vectors to capture semantic meaning. These vectors are stored in phase. You see the yellow box, which is a database optimized for finding similar vectors. On the right side of the diagram, you see what happens when a user asks a question, so a query, which is converted to the same vector format and use phase to find the three most similar document chunks from the knowledge base. Finally, we use a two-step process where Llama 7 billion summarizes the retrieved content, and then it generates an answer combining the context with the query. So the entire implementation is in GitHub and can be deployed using Colab or locally with some modifications. Here I'm going to discuss some implementation details. So an important point was memory management because of the memory restriction in the hardware platform I've used. So quantization is intended to do just that. And in order to implement quantization in this model, I'm using Bits and Bytes, which is an open source software quantizing the model to reduce the memory requirement from 13 gigabytes to 6 gigabytes GPU memory. This is a trade-off of accuracy, but gaining a lot of memory saving. Document processing and embeddings. We currently use the first 1,000 characters of each document. This is not the optimal choice, but for the start, it's good enough. For the embeddings, we use All-Mini LM L6v2, which is small memory footprint software. The vector search is done using Phase from Facebook, and it uses L2 distance metric, which is optimized for memory and speed and efficient with large memory collections. We do two-step prompt response strategy in order to conserve memory. So first step is to summarize the retrieved document and then formulate the final query for the language model to provide the response. So the key point is that we prioritize practical deployment over complexity. So let me move to a demonstration of the system. So here you see the Jupyter environment. So first thing off is to install the required components. So sentence transformers, torch, phase, py, muds. Next, you will need to, and already run all these things for you. In order to access the language model, you need to provide a token to Hugging Face, which you get from huggingface.co/settings/tokens. This is the main component of the system, which is in the form of a class. And the functionality of this class is to load the PDF files, as you see here. Then extract the test and initialize the embeddings using the sentence transformers that we discussed before, and create the index using the FAISF tool from Facebook. Initialize Llama, which is the main language model. Retrieve the documents. Summarize the text. Like I said, the queries, the documents retrieved from a database are summarized prior to creating the final prompt, and then generate the final answer. So this is the main part of the orchestrator part of the code. Here you have to modify some instructions in order to make it work for your own environment. So here I've used my own Google Drive space, so this has to be changed. And you have to, of course, mount the Google Drive, and then your PDF should be in a dedicated folder. So this can be customized by you. As you see, I've already run all these things, so I can basically enter a query, say, tell me the relation between inflation in the US and treasury yield. This is because most of the reports that I've collected are from financial press. So you see that the system is finding 3 documents because it's limited to 3 documents, rank 1, 2, and 3. And then it goes ahead and creates a summary, right? It creates a summary of this. And the summary is visible here. Yields on US government bonds reached the highest levels in over a decade on Monday, driven by concerns that persistent inflation could lead to faster than expected interest rate hikes. The 10-year settled at 3.371. So this is not really accurate. The reason is that the system is retrieving all documents, and so the end result could be suboptimal. So combining the summary with the query leads to the final response, which is here. The recent surge in US government bond yields is directly related to inflation concerns. Persistent inflation could lead to faster than expected interest rate hikes and so on. So basically correct to some extent, but not optimized, because you see here that the system is retrieving all the documents and forgetting newer ones. So let me go back to the presentation. So The current system is constrained because of hardware limitation, 512 token context window, and 6 GB of GPU RAM. It requires embeddings, summarization, which I've demonstrated before, and is truncated to 1,000 characters, which may not be the optimal choice in terms of accuracy. So it's free to use, but with significantly constrained limitations. Looking ahead, we are exploring a cloud implementation using Amazon Bedrock, and you'll see the next slide in a moment. We have the flexibility in choosing large language models and implement proper chunking, document chunking instead of truncation, without any need to summarize the embeddings prior to the main query. So moving to the next slide, which is the potential extension to Bedrock. Bedrock provides, is a tool from Amazon, and it provides choice of foundation models through a single API. It maintains the RAG capability, but with better performance. One can customize the foundation models with their own data without hardware constraints. In addition, Bedrock provides built-in support for agents, so you can create more performant applications. And for enterprise applications, it's crucial to have data security and compliance out of the box using AWS technology. So some references for the documents I've used to put together this presentation, including my own documentation and a few other useful resources for tutorials. Conclusions and next steps: working large language model RAG system. This is what we have achieved using quantization, 4-bit quantization, strategic text truncation, and made it accessible with basic GPU resources. So it demonstrates the viability of using open source large language models like Llama 7 billion parameters, FACE, and the other tools that are used in the pipeline. Finally, this work is the foundation for more sophisticated implementations in two directions. You can use your own data corpus to make it useful for your own business, for example, semiconductors, and for production deployment, for production environment, you can use the cloud, and demonstrated a little bit capabilities of Amazon Bedrock. Thank you for your attention.